appear to be delayed. Okay, good. I think it's going through. Okay, so a few things. Your progress report, the format, shouldn't deviate too much from your initial project proposal. The idea is that you want to kind of report upon what your current progress is with respect to your initial proposal, but it should still be written in the form of technical report. So it's not just a simple Q&A, but much rather, especially when your initial proposal have a lot of comments, the progress report is the opportunity for you to clarify some of those comments. Again, thinking about writing the progress report as writing a very short paper. So it should have some right context so that we understand what is your initial motivation, what you propose to do, and what is your current preliminary results, and what's your plan for the next few weeks to complete your project. So yeah, it's not just a simple bullet lists of Q&A, but much rather should be treated as a small report or a small paper that contains the information we require. Okay, any questions? Okay, so today I'm going to, as promised, to go over the technical detail behind cohomology and circular parameterization. So remember previously when we talk about time series analysis using topological data analysis techniques, the main idea is you have, say, a time sequence data. Okay, right? If you recall the time series analysis, and I can sample points from the sequence, and you take the observed function value for a sequence of windows, and that map to a high dimensional point cloud, which now what I'm showing is just a projection of this high dimensional point cloud. And then there is what's called the parameterization, which map this point cloud into S1 and then visualize it by sort of a rainbow color map. So this is red, red, I'm just trying to do that rainbow color map. Anyway, so that's the main idea. As I mentioned before, this thing is rooted from the idea of cohomology. And today we're going to go over cohomology. And it happened to be the dual version of homology. Okay. So of course, to talk about cohomology, let's quickly review homology. So the homology, now we are using some sort of notation where K is my simplicial complex. And for example, it can be a triangulation of annulus like this. This is going to be my triangulation of the underlying space. And then I'm going to use V with subscript as all the vertices, E as a subscript as all my edges, and this triangle subscript as all my triangles. Okay. So the idea, if we write it formally, but let's just look at this picture, hopefully this kind of jog your memory, is a zero-dimensional chain, which is we use C of 0 is a set, where element in the set is a linear combination of vertices. Okay. Again, we're using Z2 coefficient. Okay. so that, I'm either going from 0 to 1. So either include this vertex or not, okay? So if you look at this solid green part here, the V1, V2, and V3, those are 3 vertices. And the sum of them is my 0-dimensional chain, right? It's a linear combination of vertices. Now, one chain, which the whole set is called C1, is linear combination of edges, okay? And then in this case, we're just looking at A1, which is the linear combination of those edges in the very inner circle of this triangulated annulus, okay? So basically A1 is equal to E1, is E1 plus E2, E3, E4, E5, E6, E7, E8. It's just a linear combination, okay? So that is my 1-dimensional chain. And now the 2 chain, recall, is a linear combination of triangles. So I pick up the 2 triangle, which is triangle 1, or I call it delta if you want to, but triangle 1 and triangle 2, which is the pink, and the linear combination of them is the 2 chain. And then 2 chain usually have this notation, C of 2. This is sort of element in there, okay? Now, formally, right, if I formally write it, it's just a linear combination. So C of 0 is all the elements such that it's a linear combination of all the vertices. This is just writing it formally, where the coefficient is either 0 or 1, okay? Same thing with C of 1, capital C of 1, that is linear combination of edges with 0, 1 coefficient. And then 2 chain is linear combination of triangles with 0, 1 coefficient. So this should all look familiar. The one thing that I want to introduce is the idea of homologous. So if I have 2 elements that is coming from the same chain group, they are homologous if their difference is a boundary of a higher chain group. What does that really mean? Let's give examples. If I have A and A prime, which are both 1 chain, so they are linear combination of edges, they are homologous if their difference is a boundary of a 2 chain. What is a 2 chain? A 2 chain is a linear combination of triangle. So what is a simple example? Let's say I have, again, actually, let's just look at this picture I already have. Let's say I have A1 is my 1-dimensional chain. And now I'm going to draw a new chain in green, which is everything E1 plus E2, but it's plus, let's call this edge L1 and coming back L2. And then the rest is the same with A1, okay? So this, in some sense, this bigger chain, just kind of look like this compared to, like A1. And if I take their difference is actually the boundary of this triangle right here. Their difference is actually the boundary of this triangle. So that means those 2 things are homologous, okay? So when they're homologous, it's actually written as this notation, which basically means they come from the same class. So what that means with it when they say they come from the same class, it means that they actually bound the same tunnel in my space, okay? So if I extended in this particular example, not only the green circle is homologous to the 1 chain A1, also the orange circle this orange circle, which is a linear combination of edges, which is what I call A3, it's also homologous to A1, because if I take their differences is a boundary of all those triangles, which are the boundary of two chains and so on. Okay, so that is the picture here. So in another way to think about it, they are homologous because they're all corresponding to the same, they also all corresponding to the same generator in dimension 1 homology. This space is annulus, so there's only one tunnel, and all the A1 and A3 all bound the same tunnel, so they are homologous. Okay. All right, so now again, let's go back to this picture. And then this is a picture to keep in mind, is that if I have C2, C1, and C0, we have what's called the boundary map, right? So if I take a linear combination of a triangle, I can take the boundary, which become linear combination of edges. If I take a boundary of edge, it becomes linear combination of vertices. And let's look at the most simple example here. Let's say if this is my simplicial complex, it has 4 vertices, 5 edges, and 1 triangle. Okay, so let's call it like this. Then, an element in C2 is going to be the triangle. Let's call it triangle delta, triangle 1. So the boundary of triangle 1, and let's name those edges. Right? What is the boundary of triangle 1? It's going to be E1 plus E2 plus E3. Okay? And then the boundary of an edge, say E3, is V2 plus V3, right? And of course, there's additionally, if I take the boundary of the boundary, what is this? Can anyone recall? If I take a boundary of a boundary, what do I get?
Nothing, or 0.
0, yeah. So because I take the boundary of a boundary, the boundary of triangle 1 is a boundary, it's going to be E1 plus E2 plus E3. I take boundary of those again. So the boundary of E1 is V1 plus V2. The boundary of E2 is V1 plus V3. The boundary of E3 is V2 plus V3. So now they all cancel out because I'm using Z2 coefficient. So that's that. So the important takeaway is basically, if I take twice the boundary, I got 0. Okay. So that's what's recalled, right? So we have the boundary map, and then the one-dimensional homology is sort of the kernel of the 0-dimensional boundary map over the image of 2-dimensional boundary map, which corresponding to the what's in the cycle group quotient out boundary group in dimension 1, for example. That means it's all the cycles, but not boundaries, right? So for example, the red is part of H1 because it's a circle, but it doesn't bound anything. So of course, now let's record the boundary group and cycle group. So remember we said one chain is a one cycle if the boundary is 0, okay? So A1, if I take the boundary of A1, which is this red thing, all those endpoints cancel out. So if its boundary is 0, that means it starts somewhere and ends at the same place. It's a cycle, okay? And A2, as I just drew, the A2 is going to be the E9 plus E10 plus E11, E12, which is, the boundary of those two pink triangles. It is also a one cycle, because if I take this is equal to 0. But it's also a one boundary because A2 is the boundary of C1, right? Remember, C1 is equal to 2 triangles add together. And because A2 is a boundary of a 2 chain, therefore it's part of the boundary group, okay? But the last one is A1 is a one cycle, but it's not a one boundary because it's not the boundary of a linear combination of triangles, right? A1 is what's sort of bounding the sort of element that describe this tunnel. And this means that I'm going to use this notation to say that it's this A1 and anything that is homologous to A1 is an element of the dimension 1 homology, right? So basically it's corresponding to if I compute the dimension 1 homology of this space, it's rank 1 because it has one tunnel, and all the thing A1 describe this one tunnel, one dimensional tunnel, and everything that is homologous to A1 also describe the same tunnel. For example, A3 also describe this tunnel. Okay, so in other words, A3 is part of the equivalence class described by A1 because they describe the exactly same homology class. Okay, so that is homology. Now let's move on to cohomology. Okay, so before I introduce you all these notations, let's just have an overall picture of homology and cohomology. They are actually dual to each other. So remember, I have this notation. Okay, and with boundary maps. And then the dual of it, so this is a maps between chain groups. The dual version is a map between co-chain groups. Sorry, let me just rewrite it. I'm using subscript to denote chain groups, superscript to denote co-chain group. And then the map goes the other way, and I'm using delta as its co-boundary. So what is the notation here? C of I is chain group. And on the right-hand side, C of superscript is what's called co-chain group. B of I is a boundary group. B superscript of I is a co-boundary group. Z of I is cycle group. Z superscript of I is co-cycle group. Okay, and this symbol is for boundary, and this symbol is for co-boundary. And H of P, lowercase, is a homology group. And H superscript is a cohomology group. Cohomology group. All right, okay. Now, moving from homology to cohomology, it takes some effort, okay? So everything is as before. If I use K to be my simplicial complex, and V for vertices, E for edge, and delta for triangle, we are going to abuse the notation a little bit, where we are going to talk about what's called elementary cochain first, okay? You can imagine each of those vertices, VI, EI, and triangle I, those are elementary chain, right? Because they are just, each single element is a chain, like a single vertex is a 0 chain. A single edge is a 1 chain. A single triangle it's a 2 chain, right? So it themselves is part of the chain group. And because I'm only using one of them, they are called elementary chain. And now I'm going to abuse a notation where I put a star down there because this is easier to write later. Now the star means that they are now called elementary cochain. Okay, so far I have not really defined everything. I just put co in front of every concept we have in terms of studying homology. But elementary cochain basically are functions that takes a chain and map it to an integer between 0, 1. So another way to write it, if I'll give a concrete example here. Let's say this is V1, V2, V3, V4. V1 is an element of 0 chain. And V1 star is going to be a function that maps an element in 0 chain to an integer, okay? So I will take any V of I and is equal to 1 if I is equal to 1 and 0 otherwise. What does that mean? This means our elementary cochain is a function that operates, elementary 0 chain is a function that operates on vertices where if the vertex is itself, then it's equal to 1, and it's something else is equal to 0. Okay, so that is the elementary 0 chain. Elementary 1 chain, let's say this is my E1, I have a 1 chain that is, elementary 1 chain, which is just an edge. And then the corresponding elementary 1 chain will operate on any edges such that is equal to 1 if it's itself, right? If it's the edge self and 0 otherwise. So another way to write it is V1 star is a function that takes element from C0 and map it to Z2, and E1 star is a function go from chain 1-dimensional chain map it to an integer. And let's do one more. This is delta 1. Delta 1 star over delta I is equal to 1. Right? So delta 1 star is taking elements into 2 chain and map it to integer. Okay? That's what it does. And now, this is exactly, so what's difference between elementary chain and elementary cochain is elementary chain is vertices, edges, and triangles. And elementary cochain are functions that takes the chain and map it to an integer. So the elements that is a part of the cochain group, they are functions, okay? Before the elements are chains, here the elements are functions on chains. So this is really the biggest mind twist you need to have when you go from sort of homology to cohomology. In homology, my elements I'm operating on is sort of a linear combination of vertices, linear combination of edges, linear combination of triangles. For cohomology, what we're working with is functions on linear combination of them. Okay, so go back to what I just described. A one simplex has a corresponding 1 cochain, right? A 1 simplex is elementary chain. Its corresponding 1 cochain is basically evaluate 1 on the edge and 0 on all the other edge. So it's 1 on the edge that corresponding to this one cochain, and 0 otherwise. Okay, so that is sort of the generic writing, and that's what I wrote in the next slide. But then what we have is we can have elementary 0 cochain, elementary 1 cochain, and elementary 2 cochain. So now, same as before, once I have elementary cochains, I can define cochains as a linear combination of elementary cochains. Okay, so the mathematical writing would be, right, now an element which is in the 0 dimensional, remember it goes this way, an element in the 0 dimensional cochain is a linear combination of elementary cochain, a 0 elementary cochain. Okay, so again, I'm going to write it as a sum of elementary cochain, where the coefficient is again 0 and 1. Okay, but what is the meaning of this, right? Let's look at very concrete examples. So you have to be careful here when I say this is a linear combination of cochains, they're linear combination of functions. Okay, so let's give an example before. Okay, so actually let's go one more, like be patient with me. There's one more things that I needed to define. Now, let me write it in this way. Well, actually, let me flip the arrows to write it in this way. So those are all cochain groups. Correspondingly, I need to define co-boundary operations. And the co-boundary operations satisfy the same condition, where if I take the boundary of a 2 cochain, I obtain 1 cochain. If I take the boundary of 1 cochain, I get 0 cochain. Okay, by the end of this lecture, I'll be using the word co so many times. And then again, I mean, I have the dimension corresponding to the dimension where it's operating on. But now I would like to show you that how does this behave? Remember, let's say my beta is an element. Oh, sorry, I kind of did. That's why it's confusing. It goes from low dimension to high dimension, okay? So I have an element, beta, that is a part of 0 cochain, okay? So now what I want to do is to say if I apply the co-boundary operator on this, it has to be an element in 1-dimensional cochain. How does this work? Okay. Remember, beta is a function. You can think about delta, which is a co-boundary, also like a function. So in order to describe it, I need to apply this function to something. Okay. So what we do is we kind of evaluate, looking at what this function evaluate upon, because remember, this end result of this is going to be a 1 cochain. What does 1 cochain operate on? 1 cochain operate on 1 chain, which is edges, linear combination of edges. So let's look at how this thing behave over when it's operated over an edge, okay? So I want to evaluate it over an edge. In this case, it's edge V1, V0, V1. So let's again do a simple example. This is V0, this is V1, and V3, V4, E1, E2, E3, E4, E5, and then delta 1, okay? So that's what we have. So now the definition of co-boundary is actually, if I apply it as delta beta V0, V1, is equal to beta, where now this is where boundary comes in. Remember, they're dual operations. So I'm replacing the delta 0, I'm replacing the co-boundary operation by the boundary operation. So this is equivalent to applying beta into the boundary of the edge. So what is the boundary of the edge? The boundary of the edge, V0, V1, is V0 plus V1, okay? That's what it is. So this is basically equal to beta of 0 plus beta of V0 plus V1. And I can open it up. Okay. So what this means? This means to evaluate delta beta, which is an element over a one-dimensional cochain, is equivalent of evaluating beta over the boundary of this edge. So again, so that means the function value of this entire function operating on an edge is equal to the function of beta operating on the boundary of this edge. So for example, this will give me a value. The first beta V1 will give me a value in Z2. The second term will give me another value in Z2. And then add together, this whole thing will be a value in Z2, right? So that's why this is a function. We kind of define the function so it's operate over linear combination of edges. Okay, so now let's do one dimension higher. If I have an element alpha that is part of a one-dimensional cochain, if I take the boundary of alpha, right, is going to be an element in C2, right? It goes to the next level. So what I mean, that means it has to be a function that operates on linear combination of triangles. So let's just do one triangle here. The triangle is V0, V1, V2. Forget about this example. This example is not, it's not actually corresponding to the same index, but doesn't matter. We're just operating on elementary chains right now. So it's operating on a triangle V0, V1, V2, and it's equivalent to applying alpha to the boundary of it, because alpha is a function over linear combination of edges. So I just take the boundary of the triangle, okay? So this is equal to taking the boundary of V0, V1, V2, which is, this is equal to the alpha operating on the boundaries, which is V1, V2 plus V0, V2 plus V0, V1. And then you open it up, right? So this is a linear function, so you can operate on each individual component and sum them up. So this is actually precisely how my co-boundary operation is defined, okay? It's a little bit mind twisting, right? And let's give an example. So, okay, so let's put it another way. The co-boundary is also a very interesting operation. So if we look at this example, let's just do this example one by one. I have this triangulation with two triangles of rectangle. It has 4 vertices, 5 edges, and 2 triangles. Okay, so if I use the notation E5 star, it's C1 over Z, right? This is a function over linear combination of edges. And specifically, E5 has a value 1 on E5 and 0 on other edges. That is what E5 star means. Now I want to take the co-boundary of E5. By the definition we just saw, it actually can be written down as the co-boundary of E5 is actually the linear combination of two-dimensional cochain, which is actually corresponding to linear combination of all the triangles that have E5 and its boundary. So if you write it out, actually it's become very simple. Is if I remember, I go from 0-dimensional to 1-dimensional to 2-dimensional cochain operation. So if I take the boundary of element in C1, I will get a function over element in C2. So in order to do this, this still takes consideration of the boundary relation. And just now the delta, the co-boundary of E5 star is going to be the star of all the triangles that contain 5 on its boundary. So other way to think about it, what are the triangles that E5 is adjacent to? What are the triangles that contain E5 on its boundary?
1 and 2.
Exactly. So the definition that we just went through in the previous slide really means that if I take the co-boundary of E5 star, I will get delta 1 star plus delta 2 star. Okay. The same thing translates to lower dimensional cochain. If I take the co-boundary of V1 star right here, this is just looking at what are the edges that contain V1 in its boundary. So what are the edges? Anyone?
E1 and E2.
Exactly. So the co-boundary of E1 star of V1 star is equal to E2 star plus E1 star. So this is fairly easy rule, right? It's easier to write, but it exactly follows this math we just went through. Okay, so now you can write the co-boundary of V1 to be V1 star, the co-boundary of V3. So V3 or has 3 edges adjacent to it again. So the co-boundary of it is going to be E2 star plus E3 star from E5 star. Okay. So in another way, this sort of co-boundary operation is again looking at adjacency relation between a simplex, but adjacency in 1 dimension higher, right? Remember the boundary operation is looking at adjacency 1 dimension lower. Co-boundary is looking at adjacency 1 dimension higher. Everything else looks nice. Okay. What I would like to show is that now you have co-boundary operations. You can also define co-boundary and co-cycle. Okay, so that is the next slides here. Same thing as before. You are just replacing my boundary by co-boundary. The definition is the same. A cochain, a 1-dimensional cochain, is a 1-dimensional co-cycle if its co-boundary is 0, right? Remember in the homology sense, in cycle group is when its boundary is 0. Co-cycle group is when its co-boundary is 0, okay? And, cycle group is its boundary 0, co-cycle group is its co-boundary 0, yes. But there is co-boundary group, right? Boundary group is the ones who's bound something. So let's look at this again. Z of lowercase 1, this is called 1 cycle. That an element in here is taking the boundary of it is equal to 0. So that is 1 cycle. 1 cycle is, it goes around, right? This is 1 cycle, for example. And B of 1 is 1 boundary. Is that there exists something, let me use this A instead. There exists B that is part of Z2 such that the boundary of B is equal to A, right? Such that it's a boundary of some 2-dimensional chain. So for example, if I write a simplicial complex like this, then those 3 red edges is part of a 1 boundary because it bound a triangle. Okay. Same thing. Now, if I want to talk about Z of superscript 1 is called 1 cocycle. And 1 cocycle is just replacing my boundary operator by my co-boundary operator. And then B superscript 1 of co-boundary again, replacing my operator, is that there exists B that is one dimension lower such that all right, so the last bit we want to verify if, as before, if I take two boundary, it's 0. If I take two co-boundary, it also has to be 0, okay? So, and based on this, you can now define cohomology groups. The homology group is H1 lower script, is everything in a cycle that doesn't bound. And one-dimensional cohomology is everything in the co-cycle that doesn't co-bound. Okay, that's what it defined algebraically. Okay, and then there's also, as before, there is what we said homologous. You can also talk about cohomologous, right? Homologous, if I take the difference of these two, they become a boundary. Cohomologous is if you took sum of those two, they become a co-boundary. Okay, so there's all this duality happening, but let's look at this example. Okay, so I have the chain, one co-chain. Remember, one co-chain is going to be E1 star plus E2 star plus, oh, sorry, let me rewrite it. I have this one co-chain that is E1 star plus E5 star and plus E3 star, right? This is, again, linear combination of elementary co-chain. And what I claim, it is a one co-cycle, right? What is the condition for it to be a one co-cycle? Its co-boundary has to be 0. So I'm going to take the co-boundary of alpha. As before, because alpha is equal to E1 star plus E5 star plus E3 star, if I take the co-boundary of it, this is equivalent to take co-boundary of each individual element. Okay, and when you take each individual element, you know that this is a triangle that is adjacent to and plus a star. So what is the triangle adjacent to E1?
Triangle 1.
Yep. Put a star. What about triangle adjacent to 5, E5?
It's going to be 1 plus 2.
Exactly. Put a star right there. And what is triangle adjacent to E3?
2.
Exactly. Now just doing algebra. I have 2 copies of delta 1 and 2 copies of delta 2. This is equal to 0. So alpha is a one co-cycle. So this is also another major difference between cycle and co-cycle. Cycle has a very good geometric intuition because when I say this is a cycle, it bound something like a tunnel, right? But a co-cycle geometrically doesn't seem to be like, why is it called a cycle in some sense? But it's actually in the sense that the boundary, the co-boundary is 0, okay? So that's where the interesting thing come in. And we're going to see an example of how to compute cohomology for a torus. And hopefully that will give you more intuition of this duality, okay? But let's say you go ahead, question?
I was just going to say, so if you included E2, it would no longer be a co-cycle?
Exactly, right? If you you add E2, then E2 has another copy of delta 1 star, and that's not 0, right?
Okay. Yep, okay. Exactly.
Good. So it's all algebra, right? This is called algebraic topology. Like everything can be computed by just thinking about linear operations, okay? So yeah, so keep in mind the geometric intuition between co-cycle is a little bit non-intuitive, but let's just do algebraically. I see that alpha is a one co-cycle. It's also a one co-boundary, right? because it has to be a boundary. It has to be a co-boundary of something of lower dimension. So again, you need to think about the operation goes this way. Okay, if it's a co-boundary, if it's coming from something of lower dimension, right? So it has to be a co-boundary of a lower dimension. What's the lower dimension? Zero-dimensional cochain. Zero-dimensional cochain is, so alpha, what I claim, it's also a co-boundary because it's equal to V1 star. It's a co-boundary of V1 star plus V3 star. Why? What is V1 star and delta of V3 star? Okay, what is a co-boundary of V1 star? Anyone?
E1 plus E2.
Is equal to E1 star plus E2 star, right? It's basically all the adjacent edges and put a star on it to make it into a function. What is a co-boundary of V3 star?
E2 and E3.
And E5.
Oh, and E5, yeah.
Yeah. Put a star to make it a function. What do I have? E2 cancel out. This precisely is E1 star plus E5 star plus E3 star. That's precisely alpha. So alpha is a one co-cycle and a co-boundary. Okay, let's move on. Now let's look at my annuals. Okay, what I'm claiming now is I have this one cochain. A1. Okay, one cochain A1 is all the linear combination of the red edges with a star. Okay, so it's basically E6 star plus E7 star plus E8 star from E9 and E10 star. This is one co-cycle. Okay, so I don't know why I didn't spell out the whole thing, which I should. Okay, so I'm taking the co-boundary of it, right? I'm saying it's a one co-cycle because if I take the co-boundary of it, is equal to 0. Why? Because if you look at the E6 star, the triangle adjacent to it is delta 3, right? Put a star to it. Adjacent to 7 is 3 and 4. Adjacent to 5, E5, no, not 5, sorry, E8 is right here. This is triangle 5 and 4, right? And then adjacent to E9 is 5 and 6. Adjacent to E10 right here, it's 6. Add them all together is equal to 0. Because every single triangle in the sequence has 2 edges in this, is adjacent to 2 edges in this one cochain. Okay, so it's a one co-cycle. And then additionally, that it is not a one co-boundary. And you can again check why it's not a co-boundary, because I cannot find a linear combination of vertices such that it's a co-boundary of. Okay, so if it's a co-cycle, not a co-boundary, remember I have, if it's a one cycle, not a co-boundary, what is correspond to? It's corresponding to an element in the one-dimensional cohomology group. It's a one co-cycle that is not a one co-boundary. Okay, so again, this is where the non-intuitiveness comes in. Now, alpha 1, which is the red linear combination of edges, put a star to it. It's now an element in the dimension 1 cohomology of this space. Okay, so if you compute the dimension 1 cohomology of this space, it's going to be rank 1. Okay, but now you want to think about it. Well, if I just compute homology of this space, the rank of homology in this space, what is the rank of dimension 1 homology of this space? Anyone? 1.
1.
Because it's one tunnel, okay? What is that one tunnel? Let me draw it in a pink color. This is an example of this one tunnel, right? It can be other things, but they're all homologous. This pink edge that I just drew is, or maybe I should just draw it green just to be, yeah, I actually want to draw it pink. Okay, the pink thing corresponding to an element in one-dimensional homology, okay? It's corresponding to that tunnel. The rank of one-dimensional cohomology is also equal to 1 because that corresponding to this cohomology class, that is my red edge. And then those two things are dual to each other in a sense that if I want to compute dimension 1 homology, if I want to know the rank of dimension 1 homology is equivalent to computing in the space the rank 1 cohomology. In another way is that this red edge, so if I just drew this space in a interesting way, like this is my space, okay? What happened is that what I drew as pink, right? It's a piecewise linear thing. So what I have as pink is a representative of the dimension 1 homology. And what I drew as red is my rank 1 cohomology class. And those two things capture the same thing of the underlying space. All right. And then one more piece of information is what about cohomologous cochain? Okay. So actually this is a typo. This is one cochain. So what I drew as the red zigzag edge with a star to it is now cohomologous to the orange zigzag thing. Because if I add them together, they are boundary of something. They are actually co-boundary of a linear combination of zero-dimensional cochain. Okay, so they're homologous. So let me add one more dimension. The pink loop or pink one cycle is homologous to this green one. The red cochain is now cohomologous to this purple one. Okay. So where this is taking me, this is taking me to talk about homology groups of a torus and the cohomology group of a torus. Okay. Let's talk about let's for the time being only focus on the top part of my picture. Ignore the bottom part, just the top part. Top part of my picture, I have a torus on the right. And on the left is a triangulation of that torus surface. Okay. Why is a triangulation? Because remember, a torus can be represented by a rectangle where you glue the top piece together and the left and right together. That's how you form a torus. Okay. Now, if you look at my notation, the top edge is vertex A, B, C, D, A, B, C, and A. The bottom is A, B, C, and A. What does that mean? That means ABCA is going to glue against ABCA from top to bottom. And the left is ADE. A and the right is ADEA. So the left is glued together with the right. Left is glued to the right. So that is how the vertices looks like. And now if you think about when I compute homology, it's going to give me the two generators of dimension 1 homology that happen to corresponding to this red loop that goes around the tunnel and the blue loop that goes around the boundary of the cylinder. If I open up based on the triangulation, the red loop corresponding to AB plus BC and plus CA, right? It's just a loop. It's corresponding to the red loop. When I triangulated the torus, the blue loop corresponding to AD plus DE plus EA, okay? That's my homology. There's two homology, dimension 1 homology class that corresponding to the two tunnels in my space. Now let's look at the dual version of those. The dual version of the red loop is a zigzag pattern here. It's the same thing as this picture. The dual version of the thing that bound the tunnel is a zigzag that destroyed that tunnel, okay? So in this particular case, there is this loop, red loop goes around the major tunnel, and the dual version of it is actually, again, I'm going to draw it in red, and it's basically, I mean, of course, it goes in the back, okay? Because remember, it's all these edges add together, and then this edge is identified with this edge. So it's not just a path, but actually also a loop itself. Put a star to it, okay? So the dual version of the red is this zigzag thing that goes around the cylinder. The dual version of the blue is now zigzag going around the other tunnel, okay? So the dual version, if I drew on top of this space, the dual version of the blue tunnel is a zigzag. Of course, I'm drawing a little bit more refined triangulation, but it's this thing, okay? So it's beautiful actually in a way that if I want to compute the homology in dimension 1, I can compute the cohomology in dimension 1, where the cohomology captures the same thing as a homology, except they are represented as a functions. But hopefully by now you will get a sense of why cohomology is the one that is related to this. Because cohomology, by definition, a cohomology class is a function, right? So a cohomology class, especially a cohomology class that is an element in a dimension 1 cohomology, especially. So dimension 1 cohomology, an element in it, it's a function that takes a linear combination of edges, for example, and map it to some value, okay? So that's where things come from. So just to reiterate what I just said, homology group have these two tunnels. Cohomology is generated by alpha 1 and alpha 2. Homology is generated by A1 and A2. And alpha 1 is dual to A1, and alpha 2 is dual to A2. So the red are dual to each other, the blue are dual to each other. That is what I'm saying, it's counterintuitive, right? But this is where cohomology become important in data analysis. Remember I said, well, if I look at this torus and I parameterize it, there's two parameterization. This is the first parameterization that takes the point cloud, map it to S1, and that S1 goes around, which color did I use? I should use red. Right? This is the first parameterization. The second parameterization is the blue that goes around here. And when I parameterize it, you see that the color highlight those two homology groups, okay, in the projection. So the interesting thing about this parameterization is a kind of independent of how the quality of your embedding is, the quality of your dimensionality reduction. Because as long as you can trace out the rainbow color, it will tell you that's how there is a loop in the high dimensional space just by following this rainbow color along S1. So it turns out in order to obtain this first one, in order to get this, I'm just going to compute the corresponding cohomology that is associated, that is dual to this particular homology clause, okay? And it turns out there's a particular theory that if I use this symbol to be the set of all equivalent clauses of all the parameterization that takes a space to S1, then this is the main theorem, is to say that for me to get all the parameterization of my underlying space, when I say parameterization, just say map it to S1, it's isomorphic, which means basically in the topological sense of equivalence, to all the dimension 1 cohomology classes, right? And the only difference is that all the example I gave you is using coefficient Z2. Here, we're using coefficient Z, okay? And in this work in 2009, to obtain theta 1, theta 2 as a parameterization is equivalent to try to compute the corresponding cohomology groups in that space and turn the cohomology groups back into S1, into a visualization. Essentially, it says that if my space X has non-trivial one-dimensional cohomology, then we can construct a continuous function that represent this cohomology clause. And that's what you are seeing in the visualization. The good news is actually this code is also available online, so you don't have to go through the trouble of trying to figure this out. And then this is actually Dionysus, which if you read this paper, and one of those authors called Dmitry Morozov developed the code to do this. Well, actually also Mikhail also is one of another co-author, also wrote some code for this. So that's at the root of this parameterization. Okay. Any questions? Right. So I delay this towards the end because this is a very algebraic operation, but the duality is actually beautiful, right? It's just to say that in order for me to get a functional representation, which is exactly what I need for parameterization of the underlying point cloud, instead of working with homology, I'm going to work with cohomology, because cohomology classes are natural functions, and I'm looking for a function, right? But then those two functions corresponding to the two tunnels of the underlying space, same way as homology are, except the duality has a little bit counterintuitive thing. The dual version of the red loop is actually the one that goes around the cylinder. The dual version of the cylinder loop is actually the one goes around the big tunnel, right? So anyway, so I think this is a really cool application of cohomology in parameterizing underlying point cloud to highlight its loopy structure. And then that's what underneath the parameterization for the point cloud obtained from time series data. Okay. All right. So now let me shift content a bit. Now we have covered cohomology, and let me describe what I have in mind for the remaining of the semester. In the past, I have always set aside, say, 2 lectures where students are presenting their progress report, actually. But given that we have such a short, short semester, in a way that I'm actually going to, instead of having sort of very close to each other as a final project presentation and progress project presentation, I'm going to eliminate the progress project presentation, but I'm still expecting to see, today, after today, the really good progress report. But instead, I'm going to talk about TDAX for the next few lectures, right? So basically, how do we use topological data analysis in various data analysis and visualization tasks? We can talk about, we have already seen some of those, right? For example, in biomedicine, we're using Mapper, which is a topological tool to study genomics data, study bifurcation among cancer patients' data, right? We have also seen some application of TDA with astronomy, with signal processing. Maybe we'll talk about some TDA for material science specifically. There's topology and visualization, which we kind of touch base a little bit, which is using how merge tree, contour tree, more small complexes, those are used in visualization, but of scalar field, but also you have topology in vector fields and tensor field. A vector field is a field where on every single location there's a vector, and tensor field is at every single location there's a tensor. And tensor field arise when you study material science, when you think about the stress on a material, and then they usually call it a stress tensor because the data is represented as a matrix, basically. Okay, so I'm going to, for the next 10 minutes, to talk about one application of using TDA to study data coming from neuroscience. And this is actually co-authored by one of my undergrad students. It's part of her undergrad thesis, which is pretty amazing. It won a Best Paper Award at MICAI workshop. So the idea is what's called functional MRI. So functional MRI is the idea that you are measuring the sort of bold signal in the brain. Again, what is a bold signal? It's measure how much oxygen in certain area of the brain. And this is an interesting application of topological data analysis because we're mapping the data in two different ways. Okay, so before I talk about it, what is a key finding? The key finding is that if I map the functional connectivity information from my brain data, two different ways of mapping produce complementary information. And the topological signature we see is correlated with cognitive performance of the brain, specifically things like fluid intelligence. And you can look at how those specific ways to map the initial data such that the spatial type mapping will pick up additional behavior information and to localize the brain region that is responsible for those activities. Okay, this is all kind of, very high level, but let's talk about how do we map it. So here is what functional sort of bold signal comes out. So this is a picture of the brain on the left, okay? And you have a specific region of interest, which I call RI1. And in there, what you see is you see a bold signal, which is sort of this, think about it almost like a one-dimensional signal, and it's over time. And the one-dimensional signal is basically, on the very high level to measure the blood oxygen level, which is called bold signal. So it's corresponding to blood oxygen, something. And it's blood, so it's basically how much oxygen is going through that part of your brain, and it's obtained through image acquisition. This is when you get through a MRI machine, right? It's kind of measuring how much oxygen goes through that part of the brain. So for each different regions in your brain, in this case, there's like 361 regions in your brain, and it's measuring this bold signal. So it's there's a one-dimensional signal going from each. The classic analysis is to say this is my first signal, this is my second signal, this is the third signal. I'm treating it as a vector. Or actually, let me just use V because it's easier to treat it as a vector, right? I can vectorize this, and I can study what's called a correlation between them. And that correlation matrices will give me, so let's say each of those is a region of interest, and so on. And there is a connection if their correlation is above certain threshold. So that is a classic way of people looking at this data. And then this is called functional brain network. It's looking at the correlation between their both signal. I mean, to be fair, if you have, let's say I have like 4 ROIs for the time being, it's a click. For every pair, I can compute the correlation, right? But usually I'm going to find some threshold that I only keep the edges that is above this threshold. And people kind of conjectured, and then there's some evidence that the structure of this brain network, thresholded, corresponds to the behavior, right? For example, if I want to study autism patients, I get the brain network from an autistic patient versus a control, that the hypothesis is that their functional brain network are different. So that is a classic way. So you take, essentially, you can, if you think about this whole thing as a matrix, where each row is a region of interest, and each column is the both signal collected at a particular time, then the functional brain network is taking row against row against row against row, and to study their correlation. And what's interesting about Carey's work is that instead of thinking about row correlation, it's going to study the column correlation. It's kind of, this is what's called flip the time theory. So I'm just going to basically transpose this matrix such that now, previously, each column is a time. Now I'm going to change the column to be rows, and rows become columns. So now I'm going to take row correlation, but that corresponding to what? The time correlation. So basically we are looking at 360. So now this vector prime is now the both signal across 361 location in the brain, okay? And then now we are going to look at time correlation, okay? That gives me another network, okay? If I take row pair of row correlation, it's a network among all the, so this network on the left, this is sort of ROI. The nodes are the region of interest. This network on the right, where the node are the different times. And let's say right now I have 1180 times. So I have every single point in my network is now a time point. Okay. So that's actually what she did, is that she looks at the brain network that is looking at correlation between regions of interest and the network that is looking at a correlation between timestamps. Okay. So that's how it looks like, right? So if I look at this matrix, okay, what is the difference? Oh yeah, so this is, remember I have 1180 timestamps. This is what they call time domain connectivity matrix, because each row and each column is now a timestamp. So this is 1180 by 1180 correlation matrix. And of course, I can cluster them and try to induce a block structure out of it. And the right is the cluster results. And what happened is that if you do this, which is, like I say, it's different than the conventional, which is RI cross RI, she's looking at time domain. It's very interesting that it's now we are looking at how those time domain is matched to different parts of the brain. And basically what she's studying now is, okay, what are the places that has those high correlation and they happen to be correlated with fluid intelligence and reading comprehension. Okay. And that is really the biggest takeaway from this piece of work, is to say, instead of looking at the traditional, there's two things. So what I call time space domain is ROI cross ROI, and time domain is time step cross time step. So basically you can study both type of correlation matrices and study their correlation with behavior. And in this case, the behavior are things like fluid intelligence and so on and so forth, right? Of course, spatial domain is slightly easier because spatial domain, you have the ROI. So you know exactly the ID of the location, so you can use that to localize it. But really the main interesting takeaway is, to our knowledge, there has not been that much information about studying this signal from the time domain, and time domain provide complementary information. Okay. So this is also an example of using TDA to study specific type of graph, where in this case, the graph is coming from functional correlation of both signal. So functional MRI, right? But in next lecture, what I want to talk about is how do TDA is applied to generic graph analysis. For example, if I have graphs that is generated from different random graph model, the assumption, the conjecture is that, if they're coming from different random graph models, then there's corresponding topological signature that is obtained, for example, from persistent homology. It's going to give you very different signature. Okay, so this is hopefully is a sort of introduction towards how TDA plus graph analysis looks like. So that is something we're going to talk about in next lecture. But I want to give this example because it's actually a quite interesting finding of how to map your data in different ways and map your underlying data to a graph and then apply TDA techniques to study that graph. And we might actually go into a little bit detail of, I have not explained to me how I do that. It turns out once I map this into a correlation connectivity matrix, it's a clique, but it's a clique, or it's a fully connected graph with weights on it. So how do I apply persistent homology? Anyone have an idea? I have a weighted graph. What is the first step? Build a filtration. I have a weighted graph, build a filtration. And we have gone through a few examples of a filtration. One filtration is to say the edges show up in the order of the weights. If it's low weights, it show up earlier. If it's high weights, it show up later, or the other way around, right? You can do a sub-level set filtration of the weights, or you can do a super level set filtration of the weights, depending on what you're interested in. Or you can do a filtration based on the degree of the nodes in the graph, right? That's another filtration you can build. Depends on how you build that filtration, it gives you different signature of your underlying network or an underlying graph. Okay, so that's what we're going to talk about next lecture. And I'm going to end my recording now.